Good afternoon, everyone. My name is Adel Zaalouk, and I'm a senior software engineer in SAP. Welcome to my talk. So the title for the talk today is NetworkMachinery, a united front for network troubleshooting with CRDs. Okay, so let me go through the agenda for today. So basically what we're going to do today is we're going to discuss the state of network troubleshooting in Kubernetes. We're going to also go through CRDs and why they are useful, or what can they be used for. Can they be used for networking? And we're going to go through also a couple of use cases. So the first use case is network reachability and traffic shaping. And the second one is Kubernetized SDN. And we're also going to give 2 demos. So what's happening? So the network landscape of Kubernetes is quite complex. There's so many things happening, so many puzzle pieces. So there's DNS, core DNS with lots of plugins, the Kubernetes plugin cache, kubedns with DNS mask, DNS metrics, and kubedns. And there's also node local caching. I mean, there's also node local caching, agent debugging. There's ingress, there's services, there's kubeproxy with IPVS, IP tables. There's also a lot of components that install IP table that we need to debug. There's network policies, there's CNI. Each of the CNI needs a different debugging mentality. And there's also cloud provider networking. That's just the present. And then there comes the future. And in the future, you're dealing with IPv6, actually not that far of a future if it's not pretty here already. And there's Windows networking, and there is multi-cluster networking, and there's service meshes, there is Istio, there's the network service mesh, and so much things are going on. So if you get some part wrong, you basically have an unfunctioning cluster. Cool. So I would like to go through 2 of the previous KubeCon talks that caught my attention. The first one was titled Black Holes and Wormholes, basically understanding and troubleshooting the magic of Kubernetes networking. So they went through a couple of what they call a black hole, and basically a black hole happens when there is contract entries which are stale. So traffic is being sent to ghost pods, and the reason is because the endpoint could have died for whatever reason. And the second scenario, if you have a black hole where you forgot to set some kernel module setting, like IP forwarding, or you forgot to set network filter module, which is required to forward packets to the Linux bridges. And there's also the scenario that they talked about where it's called a wormhole. And the wormhole basically where you have conflicting IP tables because you have many components in Kubernetes that does install IP tables. And if 2 of components install an IP table rule that matches the same packet, then the packet might go to where it should not go. And you might have packet loss, and they also recommended that you should take a TCP dump on the source pod, source node, destination pod, and destination node. And this is all nice, but there were no tool proposed in this talk. And the second talk was on troubleshooting on-premise Kubernetes, underlay, overlay, and pod. And in this talk, the author talked about symptoms of network failure, actually covering also pretty similar to the previous talk, except that he talked about CNI-specific failures, like if you fail to create a sandbox, or if there's the readiness check that you're running fail. And he also talked about how you can identify network interfaces, and also how IP table in Kubernetes are coming from different sources. And he also proposed a troubleshooting tool called CocoTab, which allows you to forward traffic via an overlay tool called CocoTab. And this allows you to tap traffic from a certain worker nodes to the master node via attaching VXLAN interfaces to workers. And this is not just the 2 talks. There is a lot of other blog posts and talks about troubleshooting Kubernetes networking. But what's the problem? The problem is that there is no common place, there is no common APIs. So there's the great tools that is being implemented for troubleshooting networking just die out. So the question is how to pull in this knowledge in Kubernetes in a standard way. Enter CRDs. So if you were in the previous KubeCon in North America, there was a great talk given by Tim Hawken, and I hope he doesn't get angry that I showed his GitHub logo here. But he talked about how CRDs basically went through an evolution cycle from being just third-party resources in Kubernetes to going through CRDs, which are more mature. So you get the API server and storage for free. He also talks about the birth of the operator pattern, which is basically a declarative way of specifying an operator pattern, which is basically a way to encapsulate domain knowledge, whether it is databases, storage, or basically anything. It could be also networking, right? And then there's also the native feeling that you get as if you're defining declaratively a pod, you also get with a CRD. There's also admission webhooks and mutation webhooks. Right, so but CRDs are not just for add-ons, they are also for networking. So there's a lot of networking plugins already that make use of the concept of custom resource definitions, such as Multus, they define their own network attachment definition, and CNI Genie. And there's also Calico that comes also with a pretty much large set of CRDs. And there's also network policy, which is not itself in a CRD, but it's also falling into the context of networking. And there is also Istio that comes with a bunch of other CRDs. And there comes network service meshes and much more. But there's none for troubleshooting networking. So if you want to troubleshoot networking, you have to do it manually. So why not introduce another set that would make it easier, the life of people or developers easier to troubleshoot, right? And here comes NetworkMachinery. So the idea of NetworkMachinery is basically to utilize the idea of custom resource definition to build network troubleshooting operators. It's very familiar and widely accepted by the community. There are many frameworks available out there. Think controller runtime, think operator framework. There's also a way, it gives you a way to declaratively specify what you want to troubleshoot. Right? Instead of you saying, hey, I want to do this and that, you just imperatively you just say, I want the state of my network to end up like this. It gives you also out of the box feature set like validation, mutation, and conversion webhook, which I think there's a talk that have been given or will be given today about it. There's also versioned APIs and with auto generation, with auto code generation, and lots of the goodies that comes with adopting the concept of a CRD. So NetworkMachinery provides a collection of network troubleshooting resources. These are some of them, as it's currently in POC. So we have network traffic shaping CRD, which allows you to shape the traffic by specifying a pod and an interface, so you can inject loss or delay. We're going to also talk about it later. And there's also the network module validator. So we talked about in the previous KubeCon talks where there were the problem where certain modules were disabled. So this allows you to ensure all the time or reconcile certain modules to be up and running. And even if other teams like the security team or other team mess with these modules in the kernel, they get reconciled. There's also the network performance test that allows you to specify clients and targets and measure performance across your cluster. There's also network connectivity tests like ping, iBurf, and there's also network monitor, control, network notification to build an SDN use case. And even if you want to also benchmark your container controller network plugin, container network plugin, then you can also do so, and also if you want to generate traffic across the pods to also measure the performance of the CNI that you're using underneath. Of all these, so we're going to talk about network traffic shaping, we're going to talk about network connectivity testing, and we're going to also talk about the network monitor, control, and notification. So the first use case is basically reachability and traffic shaping. So you have, it would be nice, right, if you would specify that you have these sources in your cluster, and you would like to layer 3 check a certain destination. The destination can be an external IP, it can be a pod IP, it can be a pod name, and it can be a service. Now you might be thinking the service does not have an actual IP, it has a virtual IP. That's correct, but the service also has endpoints. So if I am to ping a service by specifying the name, then I can just say, hey, ping this service, and then the operator will just fetch out the service endpoints and then ping the endpoints. And the second use case, if you say that you want to layer 4 connectivity check, right? So in case you have network policies, it would be nice to see if your network policy is actually functioning, or after you install the network policy, you would like to generate a test just to a sanity check to make sure that everything is still running as you expected. There's also the case where you want to troubleshoot services. So kubeproxy uses IP tables to map, to do DNATing between the virtual IP of the service to the destination pods, right? And it would be nice to be able to layer 4 check the service IP, and the VIP, and then check also the backend endpoints. So if the service IP and the web and the port doesn't work, this means that something is really wrong with the mapping in the IP tables. On the other hand, if it works, then it's functioning. It would be also nice to do traffic shaping. So sometimes you want to war test or chaos test your network. So let's say you have an application that runs HTTP that has some timeouts. I want to know how this application will behave after I inject a certain loss or a certain delay. Right, so with this traffic shaper, I can just choose to inject loss or delay on specific interfaces. So let me show you a quick demo about that. All right. I think this is the right cluster. So what we have here is we have 3 pods in a deployment, and we also have 2 separate pods, and then we have a service called Demo KubeCon, which we will target. And let's look also at the CRDs. So we define network connectivity test CRDs, network monitor and network notifications, and network traffic shaper CRDs. What we're going to make use today of is the network connectivity testing. So what resources do we have? We have the network connectivity test resource, and I'm going to look at the layer 3 one first. So here, what I'm just saying is I'm saying, here's my source. I want to be able, from the API server, to reach these destinations, basically. So I have I specify the kind of the destination that I have, and I say the kind is pod, and I give the name, the namespace, and I also have kind of IP. So I give the IP is in this case external. It could be an internal IP. It could also be an IP of a node, and then I have a kind of a service. And then if I apply this. Network connectivity test. It gets applied. And I can see the result. So let's go through the result quickly. So as I showed already in the source, this is clear. And then in the destination, the result is, first of all, there's the IP endpoint result, which is just an IP endpoint. It just told you that it was able to successfully ping 888, which is a Google DNS, and it gave you also some statistics about the ping. And then it goes and fetches the pods. It shows you, I didn't specify the IP of the pod, but the operator fetched the IP of the pod and pinged all the pod that had a certain service selector. So I was able to ping these pods successfully, and then the service endpoint was also working. Sorry, the previous ones were the ones that the separate pods, and the service endpoints are the actual pods that are backing up this service. This worked fine. If I want to, let's say, if I want to change this resource, and I say it's layer 4 instead of layer 3, it won't work because there isn't a webhook installed to disallow me, because layer 4 needs to have ports defined, but I don't have ports defined. So the webhook disallowed me from really modifying this object. It would be the same if I create the object. The same would happen. It would disallow me from creating the object. So if I look at the object again, basically nothing changed, layer 3. Now let's apply a layer 4 network connectivity test to test the All right. It got successfully applied. And we can see, before we see the result, let's see what got applied. So I just specified that I want from my source API server to reach a destination service. And I just specified the service name and the virtual port, right? And in the result, what happened is I got the result for the direct service endpoint. So I made the connectivity check or the port check on the virtual IP of the service, and that worked. And then I made also the connectivity check on the back end endpoints and on the endpoints that are backing up this service, and they also work. And the nice thing that I can also do is I can inject delay or I can inject loss. So let's say I want to inject some loss in certain pods. Right? I can just define that I specify a selector of the pods that I want to inject loss in, and this selector will go ahead and apply 100% loss to a certain interface that I define, which is in this case Ethernet 0. But before we apply it, let's exec into one of the pods. All right. There's nothing applied yet. There's no loss. Now, after I apply it, let's see. Network traffic shaper. It's already there. We should be checking the network connectivity test, not the traffic shaper. Still succeeded. Let's give it some time. Let's look at the smoke ping. Let's see if it got applied to the... Okay, it was indeed applied. Okay, so now, since I applied loss to a certain interface, I was not able to ping these services because the 100% loss I applied. Now I can delete also the loss again. The traffic shaper that I have applied, inject loss. Now I deleted this guy. If I exec into the pod again, the loss disappeared because the operator cleaned it up for me. Now if I want to apply a different kind of loss, network traffic shapers, and this time it should be delay, right? Okay, now let's get the network connectivity test that we smoke ping, and I can see a delay of 200 milliseconds that was applied successfully to the endpoints or the selectors that I had, the pod that matched the selector that I had. Cool. All right, let's go back. So that was fine for just the basic testing, right? This is the first line of defense. Layer 4, layer 3 connectivity checks, fine. But what if I need more details of the network? I want to monitor my network, and I also want to be able to control my network. So basically, I want to see what's happening and take actions to do, right? Enters SDN. So SDN, OpenFlow, and SFlow, right? SDN, basically, we use this term currently for anything that is making use of networking and software at the same time. But the original definition of SDN came by making the control plane and the data plane of a network device two separate things. So the separation of the control plane and data plane, basically allowing the logic to run somewhere else, not in the device itself. And this gives the user to program their own logics, right? And then I could program a routing protocol on my own, and then basically program it into the network, and then the network would basically just use my protocol to write the packets. This was an early effort for programmable networks, and to make this happen, basically a protocol called OpenFlow was introduced. And OpenFlow is nothing but a way to specify how the traffic will be redirected, and gives you a customization on top of what the actual networking does. How it works is basically you have flow keys. You can match traffic based on source destination, source port, source IP, destination IP, source IP, destination IP, source port, destination port, and you can also do stuff like matching on Ethernet type, QoS, and then once the traffic is matched, you can take actions. You can program the actions that can be taken. You can take action to forward traffic to a controller where if the traffic is not known, and the controller can then program other rules to either drop the packet if you see that it's dangerous or it's an attack, or if you're just doing simple layer 2 learning. There's also optional actions to modify the packet itself, to set VLAN priorities, or to enqueue or send packets. So what is our goal? Our goal is to, again, monitor and control the network, right? So for controlling the network, we already talked about OpenFlow, but we also want the monitoring side. And the monitoring side can be achieved by many ways. For example, you could use SFlow for sampling traffic. You could use NetFlow. There's many other tools, but for this presentation, we're going to give an example based on SFlow. What we're trying to build is basically a control system. You have the desired and the actual result, and the desired result is having to monitor, or having a way to monitor and control your traffic. And you want to apply, for example, if I see something wrong in the network, I want to apply some rules. And these rules can be basically scaling up a pod, creating new services, or completely blocking via OpenFlow the traffic coming to this, or from this pod, or to this pod. How are we going to do this in the context of containers? There is a project called OpenVSwitch, and OpenVSwitch is basically Linux bridges ++. It allows you to do stuff like expose your interfaces for monitoring via SFlow or span ports. It also allows you to program your Linux bridges, or use OpenFlow to set flow rules. So it gives you a lot of customizability. How it works in details, just for a quick overview, the first packet comes in. I don't know how to forward it, so the kernel data path doesn't know how to forward the packet. It sends it to the user space, where it gets sent to the controller. The controller has certain logic of how this packet should be forwarded. Then a flow rule is programmed on the vSwitch or the kernel data path, and then the traffic, the second packet basically comes in and gets forwarded right away. For network machinery, these are the ingredients that we require to be able to build a prototype. So first of all, you need a CNI plugin that is based on OpenVSwitch, right? Second, you need to be able to configure and install SFlow. So SFlow needs to be running, and you need to configure OVS or OpenVSwitch with SFlow parameters. And to do this, we have a component called the SFlow OVS installer, and it's basically a config map that has the configuration parameters for SFlow, and the daemon set that runs SFlow on all of the nodes that have OVS. And the third thing, and the final thing we need are our network operators. Basically, we need a network monitor operator, and we need a network control operator. So let me show you a quick demo for that as well. All right. So let's have a look at the environment quite fast. So basically, this is all the interfaces. You can see that there is OVS installed, and these are the bridges. This is the bridge that is on the OVS system. So if I would do OVS VSTL show, it would show me that this OVS has these bridges. It has only one bridge now, and all these interfaces are basically my pods. So whenever a new pod comes in, CNI will kick in and will attach this pod to this bridge. And let's see the configuration that we have for SFlow. Currently, there is one configuration. Let's quickly delete that, because we want to install it from scratch, right? So let's. All right, so nothing. We have a clean state environment. Let's apply first the config map. Before we apply it, maybe we can have a look at it. Yeah. So basically what I'm configuring here or specifying in the config map is basically the bridge name, the collector IP, and in that case it's sflow. So I'm basically saying sflow lives on that IP. And we have the collector port, and it listens on this port. And we also have the agent IP. This is basically the bridge that will forward the traffic to the collector, which is sflow. And then you have some sampling configuration and sampling and polling. How frequent would we like to poll? So the less basically is the faster, but more CPU intensive. All right, so let's apply this guy. All right, now the next is the daemon set that we need to set. And for the daemon set, basically what it does, it runs two containers. One is an init container that configures the sflow parameters, and the second one is the one that runs sflow itself. So if I would apply that, look at the pods that I have now. It said that the first init container finished its job, and now the daemon set is running. So if I get daemon set, it's running. Let's try to reach that here. So I can see now sflow have been installed, but no values, nothing is happening at the moment. So we would like to run our operators, right? Before that, we need to start our network monitor. This is basically the controller. I'm not starting it in the cluster now, I'm starting outside. And then apply, see if it's already finished. Let's apply our network monitor. Before we apply, probably a good idea to have a look at it as well. All right, so what we're doing here is we're specifying, we're saying our collector lives in this IP on this port, and we're defining certain flows. We're defining a TCP flow and an ICP flow, and a TCP flow basically defines the IP source, IP destinations, TCP source port, and TCP destination port, and this is basically the flow keys that I want to see traffic from. In this case, I will see these keys, the traffic from these keys. What if I want to see ICP flow, I want to see just IP traffic, then I just say I need to define another flow which maps to the IP source and IP destination. And I also have the chance to define or customize what I want to see, what I want to event, basically. So I'm saying that if there is more than 100 frames per second, I would like to get notified. And this is basically the threshold section. The last section is the events config, where I say, okay, I only want maximum of five events and a timeout of 60 seconds if the event is generated. So it will be deleted after 60 seconds. I apply this. All right, I got applied. And it installed my flows, and I can already see traffic. Yep, so this is basically the traffic of my Kubernetes cluster. So one node cluster, I can see that there is a DNS talking, for example, to the API server. I can judge it by the ports, 443, and there's also other things that are going on. And I also can see that the thresholds that I defined are there. So I want, if I know that there's 100 frames per second in my cluster, 100 frames per second, I would like to get notified by an event. So the next thing that I want to see is I want to get network notifications for things that are happening. These are old ones. All right. There's nothing at the moment. So let's go and let's exec into edge ping. Yeah, this is what I want to do. I want to be able to basically float the destination IP. All right, let's run this guy. So far, there are a couple of events because the events are set to 30, but we can float here. Let's flow. Oops. Okay, things are happening now. And I can see that the traffic is being generated like crazy from my source to destination. And there's already events for that because I set the threshold to 30. So 30 is a very low value, but I can also set lower thresholds for that. And I can also see that there is already a lot of network notification being generated. Let's have a look at what the network notifications are. Okay. So basically, the network notification is telling me there is an event that has happened from a certain port, right? And there was a threshold that was defined of 30. And basically, it tells me where exactly the traffic is coming from. So what I can do now is I can just plug traffic, or I can do anything I want. And in fact, I have a controller. This is the network control controller that is basically telling me, hey, I received networking traffic from this guy. And I know where this port is. And there's a trick here, because this port is not the actual port. This is, so if I sudo show and kv switch, I can see that this port is number 7. It doesn't exist, but this is the interface index from SNMP because SFlow uses SNMP. So I can basically use another nice command to tell me the mapping that is happening between the interface index that is given by SNMP and the OpenFlow port. So if oh, that didn't copy. I run that. Let me have it in a clear way. Instead of JSON, let's have it in normal traffic. So I can see now the interface index 7 is living on OpenFlow port number 1. So if I now go and use the OpenFlow control command, I can see that number 1 was my host local, or my, one moment. Yeah, so this is basically the mapping between the interfaces and the interface index that comes from SNMP. Cool. So we managed. So in this demo, we managed to be able to build the whole control loop. We have network monitoring. We have network control in a Kubernetes context. So you can take these events, have other controllers watch in these events, and take actions. You can either scale the pod or block completely the traffic or do anything. There's other CRDs. There's also CRDs for network module validation. So I want to be able to, I want to make sure that there is certain forwarding kernel modules enabled to avoid traffic loss. Or I want to make sure, for example, in case of Calico, which makes use of our proxy, to have our proxy always enabled on the node. There's also, if I want to network performance test my cluster, I can specify, here's my clients, here are my targets, please run an iBirth test or any other kind of test. And this is basically configurable. So the status of these resources is basically like a provider spec where you can, it's a polymorphic status where it can change. So you can define your own status in a very dynamic fashion. Or even define more CRDs, which are more specialized to the use case. What is the summary? So there are many tools and patterns, but there's no API or common access point for troubleshooting. CRDs basically are a very nice, well-known community standard that enable us to describe and harmonize our APIs. And NetworkMachinery basically utilizes CRDs for network troubleshooting. It's a first line of defense to be able to do reachability and performance checks, even inject loss or delay via traffic shaping CRDs. There's also the second line of defense, which gives you more network visibility and with management and control over your cluster, so you can define a custom behavior based on network events that you receive via the operator, and also sanity checks if certain modules are enabled and so on. So this gives you a lot of flexibility. You can extend it as well if you feel like it. Finito and Uwata. This is basically my Twitter account and my GitHub handle. Check out NetworkMachinery on GitHub, and if you have any questions, just let me know. Also check out Gardener, which is basically a tool that allows you to deploy Kubernetes cluster on different cloud providers in a homogeneous and consistent manner. Thank you, everyone.